Let's begin this chapter with a quick recap of what we have learned about quadratic equations in the previous classes. We have learned that a quadratic polynomial of the form ax square plus bx plus c, a not equal to 0, is a type of polynomial. Equating a quadratic polynomial to 0 results in quadratic equation. A quadratic equation in the variable x in the form ax square plus bx plus c is equal to 0, where a, b, c are real numbers, a is not equal to 0. Example, 2x square plus x minus 300 is equal to 0. 2x square minus 3x plus 1 is equal to 0. 4x minus 3x square plus 2 is equal to 0. Note, any equation of the form px equal to 0, where px is a polynomial of degree 2, is a quadratic equation. When we write the terms of px in descending order of the degrees, then we get the standard form of the equation. Hence, ax square plus bx plus c is equal to 0, where a, b, c are real numbers, a is not equal to 0 is standard form of quadratic equation. Quadratic equations arise in several situations around us in different fields of mathematics. Let us consider a few examples. Example 1. Aditya and Linil together have 45 chocolates. Both of them lost 5 chocolates each, and the product of the number of chocolates at present is 124. How many chocolates did they have at the beginning of the game? Solution: let the number of chocolates Aditya had be 6. Then the number of chocolates Linil had is equal to 45 minus x. The number of chocolates left with Aditya when he lost 5 chocolates is equal to x minus 5. The number of chocolates left with Linil when he lost 5 chocolates is equal to 45 minus x minus 5 equal to 40 minus x. Therefore, their product is equal to x minus 5 into 40 minus x equal to 40x minus x square minus 200 plus 5x equal to minus x square plus 45x minus 200. So, minus x square plus 45x minus 200 is equal to 124, given that product is equal to 124. That is, minus x square plus 45x minus 324 is equal to 0. That is, x square minus 45x plus 324 is equal to 0. Therefore, the number of chocolates John had satisfies the quadratic equation x square minus 45x plus 324 equal to 0.
Factorization method is done in 3 ways. Splitting the middle term for ax square plus bx plus c is equal to 0. Using a square minus b square formula for ax square minus c square is equal to 0, where b is not equal to 0. Taking common factor for ax square plus bx is equal to 0, where c is not equal to 0.
At the end of this chapter, you will be able to state the standard form of quadratic equations, solve quadratic equations by factorization, solve quadratic equations by completing the square, identify the nature of roots in a quadratic equation. Example 1. Sonia's age in years 2 years ago and her age 4 years from now is 1 more than twice her present age. What is a present age? Solution: let Sonia's present age in years be x. Hence, product of her ages 2 years ago and 4 years ago from now is x minus 2 into x plus 4. Therefore, x minus 2 into x plus 4 is equal to 2x plus 1. That is, x square plus 2x minus 8 is equal to 2x plus 1. That is, x square minus 9 is equal to 0. So, Sonia's present age satisfies the quadratic equation x square minus 9 is equal to 0. We can write this as x square equal to 9. Taking square roots, we get x is equal to 3 or x is equal to minus 3. Since the age is a positive number, x is equal to 3. So, Sonia's present age is 3 years. Example 2. X plus 2 whole square minus 9 is equal to 0. Solution. We can write it as x plus 2 whole square is equal to 9. Taking square roots, we get x plus 2 is equal to 3 or x plus 2 is equal to minus 3. Therefore, x is equal to 1 or x is equal to minus 5. So the roots of the equation x plus 2 whole square minus 9 is equal to 0 are 1 and minus 5. Observations. In both the examples above, the term containing x is completely inside a square, and we found the roots easily by taking the square roots. Equations like x square plus 4x minus 5 equal to x plus 2 whole square minus 9 is equivalent to x plus 2 whole square minus 9 equal to 0. In fact, we can convert any quadratic equation to the form x plus a whole square minus b equal to 0, and then we can easily find its roots. Let us see how x square plus 4x minus 5 is converted to x plus 2 whole square minus 9. So, x square plus 4x minus 5 equal to 0 can be written as x plus 2 whole square minus 9 equal to 0 by this process of completing the square. This is known as the method of completing the square. X square plus 4x is equal to x square plus 4 upon 2x plus 4 by 2x equal to x square plus 2x plus 2x equal to x plus 2 into x plus 2 into x, x plus 2 into x plus 2 into x plus 2 into 2 minus 2 into 2 equal to x plus 2 into x plus x plus 2 into 2 minus 2 into 2 equal to x plus 2 into x plus 2 minus 22 equal to x plus 2 whole square minus 4. So, x square plus 4x minus 5 equal to x plus 2 whole square minus 4 minus 5 is equal to x plus 2 whole square minus 9. So, x square plus 4x minus 5 equal to 0 can be written as x plus 2 whole square minus 9. In brief, this can be shown as follows. X square plus 4x is equal to x square plus 4 by 2 whole square minus 4 by 2 whole square equal to x square plus 4 by 2 whole square minus 4. So, x square plus 4x minus 5 can be written as x square plus 4 by 2 whole square minus 4 minus 5, that is x plus 2 whole square minus 9 equal to 0. This formula for finding the roots of a quadratic equation is known as the quadratic formula. Consider the quadratic equation ax square plus bx plus c equal to 0, a not equal to 0. Dividing throughout by a, we get x square plus b upon ax plus c upon a is equal to 0. This is the same as x plus b upon 2a whole square minus b upon 2a square plus c upon a is equal to 0. That is x plus b upon 2a whole square minus b square minus 4ac upon 4a square is equal to 0. So the roots of the given equation are the same as those of x plus b upon 2a whole square minus b square minus 4ac upon 4a square equal to 0. That is those of x plus b upon 2a whole square equal to b square minus 4ac upon 4a square. If b square minus 4ac is greater than or equal to 0, then by taking the square roots in 1, we get x plus b by 2a is equal to plus minus square root b square minus 4ac upon 2a. Therefore, x is equal to minus b plus minus square root b square minus 4ac upon 2a. So, the roots of ax square plus bx plus c are minus b plus square root b square minus 4ac upon 2a and minus b minus square root b square minus 4ac upon 2a if b square minus 4ac is greater than or equal to 0. If b square minus 4ac is less than 0, the equation will have no real roots. Thus, if b square minus 4ac is greater than or equal to 0, then the roots of the quadratic equation ax square plus bx plus c equal to 0 are given by minus b plus minus square root b square minus 4ac upon 2a. Let us consider some examples for illustrating the use of the quadratic formula. Example 1. Find two consecutive odd positive integers, sum of whose squares is 290. Solution. Let the smaller of the two consecutive odd positive integers be x. Then the second integer will be x plus 2. According to the question, x square plus x plus 2 whole square is equal to 290. That is, x square plus x square plus 4x plus 4 is equal to 290. That is, 2x square plus 4x minus 286 is equal to 0. That is, x square plus 2x minus 143 is equal to 0, which is a quadratic equation in x. Using the quadratic formula, we get x is equal to minus 2 plus minus square root 4 plus 572 upon 2 equal to minus 2 plus minus square root 576 upon 2 equal to minus 2 plus minus 24 upon 2. That is, x is equal to 11 or x is equal to minus 13. But x is given to be an odd positive integer. Therefore, x is not equal to minus 13, x is equal to 11. Thus, the two consecutive odd integers are 11 and 13. Verification. 11 square plus 13 square is equal to 121 plus 169 equal to 290. If b square minus 4ac is equal to 0, then x is equal to minus b upon 2a plus minus 0. That is, x is equal to minus b upon 2a or minus b upon 2a. So, the roots of the equation ax square plus bx plus c equal to 0 are both minus b upon 2a. Hence, quadratic equation ax square plus bx plus c is equal to 0 has two equal real roots in this case. Note, if b square minus 4ac is less than 0, then there is no real number whose square is b square minus 4ac. Hence, there are no real roots for the given quadratic equation in this case. Since b square minus 4ac determines whether the quadratic equation ax square plus bx plus c is equal to 0 has real roots or not, b square minus 4ac is called the discriminant of this quadratic equation. So, a quadratic equation ax square plus bx plus c equal to 0 as 1. Two distinct real roots if b square minus 4ac is greater than 0. 2. Two equal real roots if b square minus 4ac is equal to 0. 3. No real roots if b square minus 4ac is less than 0. Let us consider some examples. Example 1. Find the discriminant of the quadratic equation 2x square minus 4x plus 3 equal to 0 and hence find the nature of its roots. Solution. The given equation is of the form ax square plus bx plus c equal to 0, where a is equal to 2, b is equal to minus 4, and c is equal to 3. Therefore, the discriminant b square minus 4ac is equal to minus 4 square minus 4 into 2 into 3 equal to 16 minus 24 equal to minus 8 less than 0. So, the given equation has no real roots.
Relation between the roots and coefficients. If alpha and beta are the roots of the quadratic equation ax square plus bx plus c is equal to 0, then alpha plus beta is equal to minus b upon a and alpha beta is equal to c upon a. Sum of the roots is equal to minus b upon a is equal to minus coefficient of x upon coefficient of x square. Product of the roots is equal to c upon a is equal to constant term upon coefficient of x square. 2 from quadratic equation if its roots are given. If alpha and beta are the roots of the quadratic equation in variable x, then x is equal to alpha and x is equal to beta. X minus alpha is equal to 0 and x minus beta is equal to 0. Whole bracket x minus alpha, whole bracket x minus beta is equal to 0. X square minus whole bracket alpha plus beta, x plus alpha beta is equal to 0. That is, x square, sum of the roots, x plus products of the roots is equal to 0.